Hello, in this video we're going to mainly focus on the Laplace transform and how it works with derivatives. We've seen this a little bit in our previous work, but we're going to derive the important fact for second derivatives in this video. And just as a reminder about the Laplace transform, it's a linear transformation in the sense that it's linear like differentiation and integration. It's a transformation that you input a function to and you get out a function, just like taking derivatives or integrals. And like differentiation and integration, we can do the Laplace transform term by term, and we can pull out constants. The definition of the Laplace transform of a function of t is given here, where it's it's the definite integral from 0 to infinity of e to the negative st times f of t. Alright, so and just notice that the Laplace transform of a function of t yields us a function of s, and we write that as indicated down here kind of at the bottom. Right, it transforms a function little f of t to something we like to refer to as big F of s, or if we're talking about y, a little y of t a lot of times is going to be the unknown for our differential equations. Then we would write the Laplace transform of little y is equal to big Y, and we can kind of view it this way here as well. But we have these important linearity properties illustrated here in number 1 and 2 up above, in that the Laplace transform can be done term by term, and constant factors come along for the ride. So C we're thinking about as a constant factor, F being the function of t. If we combine 1 and 2 together, we get this other related fact, right? The Laplace transform of linear transformations is linear transformation of the Laplace transform. Alright, so now we're going to see how that works with differentiation. Alright, so this is going to be important to understand, to have these facts at our fingertips when we solve differential equations via the Laplace transform method. So at the top, I've wrote down the definition for the Laplace transform, and now I'm going to apply it. We're thinking about applying this with the function little f of t being the derivative of our function y. And again, this is going to be applicable when we solve first and second order differential equations. Alright, so I'm going to do some of the derivation here, and then we're just going to apply this fact afterwards to then derive the fact for second derivatives. Alright, so what we do here is I just use the definition. So we're substituting in dy dt into the integral defining the Laplace transform. Alright, next we're going to rewrite this to evaluate that definite integral by using integration by parts. Alright, remember, with integration by parts, that's reversing the product rule, but a lot of times you're used to from Calc 2 this u dv notation. So what we're going to do here is we're going to define u to be e to the negative st and dv to be the rest of the integral here. I've got that typed in below. Alright, so now remember, when we do integration by parts, we have to take the derivative of u, so that's going to give us negative s e to the negative st dt. Alright, and we also have to take the antiderivative of dv, that gives us v, while the antiderivative of dy dt is just going to be y, or y of t. Keep in mind here we're differentiating and anti-differentiating with respect to t. Alright, so now what is the integration by parts formula? If you remember, it's u times v, no derivatives, no integrals, and then for us it's going to be minus the integral. In this case, it's a definite integral from 0 to infinity of v du. Right, and also we have to evaluate the u times v from 0 to infinity. Okay, so let's substitute that in this expression here. Alright, so we have the Laplace transform of the first derivative. I'll leave off the dependence on s, is going to equal the integral from 0 to infinity of e to the negative st times dy dt. Alright, now using integration by parts, it's going to be u times v, so that's going to be e to the negative st times y of t. Okay, keep in mind that we've got to evaluate this from t equals 0 to infinity. Alright, that's a limiting process. Minus the integral from 0 to infinity, and then it's going to be v du. Well, v for us is y of t, or just y, and dv is negative s times e to the negative st dt. All right, now let's go through and just evaluate here. Now, for this evaluation, so we're just about done with this, but for this evaluation here, we have to plug in infinity, which means take the limit as t goes to infinity. All right, so technically what we have to assume, and this is a fact you'll see in various textbooks, is that we have to assume that the function y of t is what we call exponentially bounded. All right, if there exists some number so that is bounded by an exponential function. All right, now if that's exponentially bounded, then the limit as we go to infinity will be 0. So this first part, when we, roughly speaking, plug in infinity or take the limit as t goes to infinity, will give us 0. All right, assuming y is an exponentially bounded function. Most of the functions we know about are exponentially bounded. And then we would subtract what we get by plugging in 0, which will be e to the negative s times 0, which would be 0 times y of 0. So we're plugging 0 in for t there. In this second integral, notice this negative sign, this negative s factor, I should say, we can bring outside of the integral because s is a constant, right, in regard to this integration. So that negative s will come out and make that addition, and then it'll be s times the integral from 0 to infinity of y of t times e to the negative st dt. All right, now we're essentially done, but we just have to recognize that this integral we have here is actually the Laplace transform of the function y of t, or just the Laplace transform of y. All right, now what's e to the 0? That's 1, so that's good. All right, 0, forget about that. So what is this turning into then? On the left-hand side, we have the Laplace transform of dy dt. On the right side, what do we have? We have minus y of 0 plus s times the Laplace transform of y. Okay, now that's not typically how you're going to see that written. A lot of times these two terms here are reversed, and in the table I'm going to show you in a minute, that is what we'll see. So it's s times the Laplace transform of y minus y of 0. Okay, so we're going to be using this fact quite a bit when we work with first and second order differential equations. We take the Laplace transform of both sides. We're going to convert the Laplace transform of the first derivative into this expression, which involves s, the Laplace transform of y, and the initial value y of 0. Okay, so again, I'm just going to show you the table of Laplace transforms that I'm going to be sharing with you, and I have this fact towards the bottom of that. It's the second to last row. So on the left hand side we have the function that we're taking the Laplace transform of. On the right hand side is the result here. So it's s times the Laplace transform of y minus y of 0. Sometimes we're going to write down, instead of writing the Laplace transform of y, we're going to write capital Y of s. So this is just another way to express the same fact. Alright, now I've got in the last row of the table the result for second derivatives. So let's derive that. Okay, so we've got this fact already taken care of. Alright, now we're just going to derive the second fact based on that one, and the fact that differentiation is a repeated process. Meaning, if I look at, and we want to know what is the Laplace transform of the second derivative of y with respect to t, then notice that that's really the first derivative of the first derivative. Okay, so now what we're going to do is just apply the above fact to the first derivative here. Alright, so what does the above fact say? It's going to be s times the Laplace transform of your function, right? Because we're saying this is, now we're thinking about dy dt playing the role of y up above, minus your function evaluated at 0. Well, what's our function? Our function is dy dt. So we have to evaluate that at 0. And our function we have inside of here is also dy dt. Alright, now we're going to apply the fact again. So now essentially what we're going to do is take this result from up above here, and we're going to plug it in down below. Alright, in for the Laplace transform of dy dt. So directly substituting that in now, we get s times, let's leave ourselves a little bit of space for that, it's s times the Laplace transform of y minus y of 0. So we get s times the Laplace transform of y minus y of 0. And then we still have this other term at the end here, which I'm just going to write it using the prime notation now. So instead of dy dt, I'm going to write y prime of 0. Now, to get the fact that I have listed in the table, you'll see listed in textbooks and videos, distribute the s through the parentheses there, and we get s squared times the Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, so combining that together, what we started with was the Laplace transform of the second derivative, so I'll just use double prime. And now what we're seeing is we can express that as a linear combination of the Laplace transform of y, s, and the variable s, and the initial values of the function and its first derivative. The initial values are always going to be at 0 here. Alright, so that's it. Now again, referencing the table here, I've got that fact written over here in the table. So on the left side, I'm saying, alright, that's the Laplace transform of the second derivative. On the right side, we've got the result. That's it for this video.